Hi, welcome to the parallel universe. Kirchhoff's voltage law, that is KVL, states that in any closed loop of an electric circuit, the algebraic sum of all potential differences, that is amps and voltage drops, is zero. Means the total EMF is equal to the total potential drop across the resistors. This is based on the conservation of energy, that is, energy cannot be created or destroyed. If I amount of current is flowing through a loop having resistor R due to the driving cell E, then E is equal to IR.
In this circuit there are two loops. First loop is A, B, E, F, A. And the second loop is B, C, D, E, B. In loop 1, due to the cell E1, the current flowing I1. Because of this, the voltage drop across resistor R1 is VR1, which is equal to I1 multiplied by R1. Similarly, in the second loop B, C, D, E, B, due to the cell E2, the potential drop across the resistor R2 is VR2, which is equal to I2 multiplied by R2. It is to be noted that in the branch BE, I1 is flowing vertically downward, whereas the current I2 is flowing vertically upward. If we consider that the magnitude of I1 is greater than I2, then the resultant current will flow vertically downward with a magnitude I1 minus I2.
Now, before applying KVL, we need to consider 2 points. Number 1. If current flows along the same direction to the loop considered, the potential drop is positive. But if current flows along the opposite direction to the loop considered, the potential drop is negative. Number 2. As per the sequence of the loop, if we touch the positive terminal of the cell, then EMF should be marked as positive. But as per the sequence of the loop, if we touch the negative terminal of the cell, then EMF should be marked as negative.
Now, let us consider the loop A, B, E, F, A. We start from the point A. When we travel from A to B across the resistor R1, the potential drop is I1 multiplied by R1. Remember, here the direction of current is along the direction with the loop, hence positive. Now, when we travel from B to E across resistor R3, potential drop will be I1 minus I2 multiplied by R3. Once again, check that the direction of current is along the direction with the loop, hence positive. When we travel from E to, there is no resistor or cell. But when we travel from F to A, we touch the negative terminal of the cell E1. Hence, E1 is marked negative.
Similarly, for the loop BCDEB, let us start from the point B. If we travel from B to C across the resistor R2, the potential drop is equal to I2 multiplied by R2. It is to be noted that the direction of the current is aligned to the loop, hence positive. Now, if we travel from C to D, we touch the negative terminal of the cell E2 first. That's why we need to mark E2 as negative. Then, on the way from D to E, nothing is present. But if we travel from E to F, we may notice that the direction of the net current is in the opposite direction to the loop. In this case, the potential drop across the resistor R3 is equal to I1 minus I2 multiplied by R3, but with a minus sign.
Thus, if we combine both the loops, we will get two equations. Solving them, we can predict the amount of current. or we can predict the value of unknown resistors. Hope you have enjoyed this video explanation. Happy learning. Enjoy learning.